Morning, everyone. I'd like to thank the Lake Committee, the Tech Committee, for giving me a chance to speak here today. I really appreciate the support we've gotten for our program across the board. It's allowed us to do a lot of work beyond what we've accomplished in the past. Today, what I'm going to talk about is an effort to go beyond some of the stuff we've done in the past and start looking at factors that might be contributing to these lakes looking the way we look, to them being perceived the way we perceive them. It's a pretty long author string, but these three agencies, Fish and Wildlife Service, Michigan DNR, and USGS, have been collaborating a fair bit in the past several years in getting lake-wide acoustic surveys done on Michigan and Huron, and up on Lake Superior. USGS has been the key in the past few go-rounds. So I'm going to talk to you today about how environment and space appear to structure the fish communities in the three upper lakes. Historically, these lakes have been viewed as falling along a trophic gradient. Work going back to Vollenweider's paper from '74 talked about how we could place these lakes on the gradient that basically led from Lake Superior, the most oligotrophic, to western Lake Erie as the most nutrient rich. In addition to that trophic gradient, I would argue there are a lot of other gradients that we haven't even thought of that are important. Those gradients are efforts we have looking at these lakes combined present an opportunity for experimentation and ecological research at a scale that is really unique. And I don't think we think about that enough. I mentioned this trophic state gradient. We've seen in some cases divergence and convergence depending on where we're looking. Recent paper talks about the convergence of trophic state in the three upper lakes. Rick Barbiero wrote that. We've also seen in recent years a paper that I think is really cool talking about stress across all the Great Lakes. And I don't mean stress of fishery managers who have to deal with low numbers of alewife or arguing there are low numbers of alewife. I'm talking about environmental stress. There's also, we're fairly clear on, a gradient in fish community composition that as a rule runs from mostly native in Lake Superior to not so much the southernmost lake. Ultimately though, the thing that I'm trying to do to go beyond what we've done in the past except for very few examples, is to start looking for patterns and processes in data we have from all three of these lakes. And that became an opportunity because in 2011 we had lake-wide acoustic surveys that happened in all three of the upper lakes. They were separated by 1 month in the case of Huron and the other two, which made for some difficulties in selecting some of the data to analyze, but ultimately I think it's a pretty important opportunity, and that opportunity has been afforded us by CSMI work. So thinking about these pelagic fish communities, there's recent evidence, both published and unpublished, that we have relatively similar biomass density in the three upper lakes, which some people have argued, including Daniel, points to a degree of convergence that goes beyond just lower food web convergence. I'd argue, though, that the differences that we have in the lakes that we talk about in the lakes are pretty poorly characterized, and we've not spent a whole lot of time thinking about or identifying which species actually drive the differences in these lakes and what types of differences actually exist. And there have really been few lakescape efforts, if you want to use that term, to look at this type of question. I've tried to do it at a couple of different levels with a couple of different tools in past years, and ultimately those efforts also involved surveys that were done with acoustics. So I think that drives home for me this idea that acoustic sampling, while we can use it to feed into these stock assessment models that we might develop, we can also use it for other things. So I started out with this based on what I know about the lakes with a basic hypothesis set. First, that the fish communities in the three upper lakes were going to be different in location, in ordination space, not location. Lake Superior is northwest and Lake Huron is southeast. But also they would differ in dispersion. That's if you put the points from the locations in the lake in an ordination plot for a particular lake, there's going to be more or less spread in those points. And I'd argue that because of the greater diversity in Lake Superior, there should be more dispersion in Lake Superior. And finally, I think based on what I know, I felt it was reasonable to conclude that most of the differences that we see were spatially structured environmental drivers, and that some of those are very clear and some of those are not very clear. This was an opportunity to make sure that my thinking is correct, that these are spatially structured environmental drivers, and then to start working on identifying them. So the explanatory variables I ended up with that I felt comfortable with and thought were founded in reality is environmental stress. There's a nice paper from Allen et al. That talks about environmental stress in the Great Lakes. Was able to obtain a GIS layer from that paper. Chlorophyll, the basic idea is more chlorophyll equals more zooplankton, which should equal more fish. Euphotic zone depth is just kind of a measure of water clarity, and I think that's likely related to the predation risk and access to food for the different species we're dealing with. Temperature, metabolically important. These species we're talking about all have specific preferences. And finally, bottom depth. From work I've done in Michigan and Huron and work Dan Ewell's done in Lake Superior from these acoustic surveys, it's pretty clear that bottom depth is important. I'm not going to argue that we know exactly how important or why it's important, but these seem pretty reasonable to me. So to give you an idea of what I'm talking about with ecosystem stress, this is from this Allen et al. Paper, and you can see basically the more pink the lake is, the more stressed it is. And I'm not sure anybody's really surprised about this, especially if you've seen the paper. It's a pretty cool paper. I strongly suggest you read it if you haven't. Another way of thinking about things, this is euphotic zone depth, calculated from data, 4-kilometer resolution data that I got from NASA Ocean Color website. And you can see that within Lake Michigan or any of the lakes, there's a gradient in euphotic zone depth that's not insignificant, to say the least. I'm not sure yet how it varies spatiotemporally, but it does vary within lakes at any given time. So the data types and sources, specifically the fish community data, the acoustic surveys in 2011. These are the boats right here that were involved. I left out the kayak because I didn't have a picture of it. Sorry, guys. But these white points in this map here, those are the acoustic survey locations during those years, and basically each one of those represents a fish community relative abundance data point. As I said earlier, I used NASA Ocean Color data to get chlorophyll, PAR, euphotic zone depth, and SST. PAR I've got here because I considered it, but I couldn't include it because it changed from one month to the other. Bottom depth came from the acoustic surveys. It's pretty easy to get bottom depth from those. And in terms of how I did this, the first hypothesis was this idea that the fish communities differ in composition and diversity. I used redundancy analysis basically as a way to visualize the data, look where the lakes fell in ordination space. I took it a step further than looking at them, and I used something called PermANOVA, which is a permutational version of ANOVA for multivariate data. So that tells us that there is in fact a significant difference among lakes. It allows you to test that hypothesis. And this measure of dispersion here, as I mentioned earlier, that's just what kind of spread there is for each of the individual lakes. So if we move to an ordination plot here, we have just our first and second ordination axes, and each dot is a transect location, the mean value for a transect, and the polygons show the different lakes, with Huron being that sort of pink or magenta, Michigan being black, and Superior being blue. And what you can see here is that the lakes are in fact visually distinct, with the exception of a little bit of overlap here between Michigan and Huron. What I've also plotted here, though, to help us understand what is contributing to or driving these differences, I've shown how the species sort of load on these different axes. And you can see way over here, the thing that is basically driving Lake Superior to be where it is, or these lakes to be where they are on this first axis, is Kaiai. And that's, I think, a pretty important point, because I think most people might not have thought that. I didn't think that. I was thinking it would be Cisco. But the simple fact is, the most numerous fish in the pelagic zone of Lake Superior is not Cisco, it's Kaiai. Biomass is a different story. So that, along with another set of species, helps push these lakes where they are. In the case of Lake Michigan, I don't think anybody's surprised that it's alewife that's driving Lake Michigan in this direction on this axis. And in the case of Lake Huron, these two, I think we were shown pretty clearly yesterday by a presentation Tim O'Brien did, that community is dominated by those two fish. We also have a smattering of emerald shiners in there as well, but they're very near the origin, kind of like Cisco. So looking at this, it seems like there are probably differences. Statistically speaking, there are differences that are significant in their location, where the lakes fall in ordination space, and there are also significant differences in the spread of the individual lakes. So they're different in a couple of ways. And that's, I think, to me, an important conclusion to keep in mind. So hypothesis 2, the idea that the cause for these differences was going to be primarily spatially structured environmental variation, is one that I looked at using a bit of an extension of redundancy analysis, which is basically like a partial multivariate regression. And what this allows you to do is it allows you to look at different sources of variation using 3 or more data matrices, one being your community matrix, one being your environmental variables, and one being the spatial representation of your data, which in this case was a polynomial trend surface of the latitudes and longitudes. So this look at multiple sources, though, you can look at, by doing a partialing of the variance, you can look at non-spatially structured environmental influence, you can look at spatially structured environmental influence, non-environmental spatial structure, and finally residual. And what I'm arguing is that this category here, most of the variation should fall in this category. If we look at this another way, this graph shows the different categories that I'm thinking about. A, B, C, and D correspond to these 4 bullets. Ultimately, my point is, I think the variation that falls right in here is going to be the greatest, based on what I know about these lakes. And if we take a look at this plot, all I've done is add to the previous plot the environmental variables that I've determined in this analysis that are influential or are important in driving the community structure, or correspond with the community structure if you want to look at it more conservatively, and remember that correlation is not causation. Ultimately, I don't think some of them are terribly surprising, but Kaiai and depth go hand in hand. They're, as I mentioned earlier, the most numerous fish in Lake Superior. Where they occur is deeper than any of the other lakes. We don't even have depths of Lake Superior's depths in some of these other lakes. So I also think that it's pretty straightforward to think about the stress and water temperature, sea surface temperature, as being important corollaries for this alewife community in Lake Michigan here. And again, that's not the stress dealt with by the fishery managers, it's the environmental stress. So the thing that is interesting here, though, is these fish in Lake Huron are intermediate. What you're looking at, the direction of these arrows tells you, what the the size and the direction of the correlation is the arrow is in a positive direction. So we have both of these two lakes somewhere in the same area in terms of stress. And the bottom line, though, is we're looking at temperature, stress, and depth that have some influence on these fish communities. And this plot, a Venn diagram, shows in one circle the purely environmental variation. The second circle, that's sort of a yellow color here, the purely spatial variation. And where they overlap, it's spatially structured environmental variation. And there's numbers I've got here that basically show what proportion of the variation is explained by each of those categories. We see that the vast majority of the variation in these three lakes is explained by spatially structured environmental variation. We can see that there is a fair bit that's relatively consistent here of purely spatial or purely environmental variation. And we can also see that there's a fair bit of residual variation. But if you want to look at this in a sort of regression approach, you sum up these numbers and these three numbers, and that's basically your overall R squared. So what this tells us is that we explain over 70% of the variation in the communities in these three lakes with the variables that I've included. The take-home messages for me are that the only reason we could do this is because we had lake-wide surveys in each of these lakes in the same year. We don't get to do that every year. And I would argue that this kind of work is something that we should be thinking about, every time we have the opportunity, whether it's because of CSMI or a change in how a particular lake's crew is going to deal with CSMI. We need to find something that's bigger picture across all the lakes that drives a theme for CSMI, and this kind of spatial analysis to help us understand process is important. Structure is important. Communities are very different. So we know that statistically and from our gut now. I think that's not unreasonable. My hypothesis was supported that most of the variation was spatially structured environment, but there's also small but significant purely spatial and purely environmental components. And one of the things that I need to do next is to build on what I've done here. At the scale of these three lakes, we see there's this structure. Can we bring it down to the single lake level and see if there's consistency within the single lakes? And that's the next step for me. And finally, bottom depth, stress, and temperature were the primary environmental drivers. I think we really need to look into more the mechanisms behind these. Some of them I think I have a handle on. Chi and depth, well, that's got to do with where mysis is located. That's a no-brainer for me. Stress is not completely an innocent bystander here, but I'm not arguing that because Lake Michigan is stressed, we have alewife. It's stressed because we have alewife. It's stressed because we do a lot of things to this lake that we don't do to the other lakes, including stocking of non-native fish. So the key is to try and put it in a context that's, I think, reasonable. I don't feel like we need to be telling people that, oh, this lake is so stressed that, this is why we see what we see. It's not that simple. Finally, temperature, I think, is a no-brainer. 2014 was even more so a case where we could see temperature impacts on the fish communities and their structure. And I do know that when I do collapse down to individual lakes and look at this, that both bottom depth and temperature remain drivers of community compositions in space. But the thing that falls out is stress. So with that, I'll again say thanks for the opportunity to speak to you today, and I think maybe I have time for questions.